Okay, so we have come up with a prescription to build a sequence of polynomials which are orthogonal with respect to some weight function in some given interval. And so in this lecture we will see, just based on these uh, properties which come from first principles, it's possible to write down a general recursion relation that orthogonal polynomials of this kind satisfy. Okay, so we start by writing down a generic nth degree polynomial, right? So our nth degree polynomial is, has a bunch of coefficients like this. Cn of x is equal to some summation over r going from 0 to n. It's a degree n polynomial. So, and an r x to the r. Now if you multiply throughout by x, we get a polynomial of degree n plus 1, right? So we have x times Cn of x is summation over r going from 0 to n, a and r, these coefficients. So this r here is superscript r is not a power, it's just that there are these two parameters associated with these coefficients, right? So a subscript n superscript r and x to the power r plus 1, right? So it's convenient to write the same sum as in terms of r going from 1 to n plus 1 and a n r minus 1 x to the r, right? So all we have done is shifted r plus 1 to some other dummy variable. If I call it s, then r will become s minus 1 and s will go from 1 to n plus 1, and then there's no need to call it s, we might as well just call it r, right? So that's how we get this. But Cn plus 1 is another n plus 1 degree polynomial, right? So I mean, we have one n plus 1 degree polynomial, and the idea is that we want to compare this n plus 1 degree polynomial we constructed from the nth order polynomial with respect to the n plus 1 degree polynomial itself, which for which we have this expansion, right? So in terms of same kind of notation, but now you see I have the superscript is r and the subscript is n plus 1, right? So it corresponds to this n plus 1 polynomial, and r will now go from 0 to n plus 1, and of course you have an x to the r sitting here. So now if we compare these two polynomials, and in fact we look at a particular combination of these two. So what we do is, you take this polynomial Cn plus 1 and then multiply this x times Cn plus 1 of x by a suitably chosen factor. So we have a n plus 1 n plus 1 divided by a n n, right? And then times x times Cn of x. So now comes a crucial argument, right? So what we're doing is trying to peel off this highest order term, right? So what do we, so we know that Cn plus 1 has this highest order term, which is given by when you put r is equal to n plus 1, and so that's going to be a n plus 1 and x to the n plus 1. So we want to come up with a way to remove this highest order term, n plus 1 term. So the highest order term here is a n plus 1 and n plus 1, and the highest order term here is when r is equal to n plus 1. So if r is equal to n plus 1, we get a n n. So if you take C n plus 1 of x and then subtract this factor times x times n plus x times n of Cn of x, then indeed we are guaranteed that the result cannot be a polynomial of degree greater than n, right? So I mean, because we have peeled off explicitly the n plus 1th order term, so there is no question of the n plus 1 order term surviving. So in general, you have a degree n polynomial, and we know that these orthogonal polynomials form a basis for all polynomials up to degree n. So you can consider this nth degree polynomial on the right hand side and expand it in terms of these basis functions. So you can always find a set of coefficients delta I, where I runs all the way from 0 to n, such that this summation delta I Ci is indeed the polynomial that you want to extract. It's an nth degree polynomial. All these coefficients delta I are for sure possible to find. And in fact, it turns out that not all of these coefficients are going to be non-zero. So in fact, we will presently argue that at best there are two coefficients here which are non-zero, and they correspond to I equal to n and I equal to n minus 1. So delta n and delta n minus 1 are are the only potentially non-zero coefficients. In other words, delta I for all I less than or equal to n minus 2 are for sure going to be 0, right? So we are going to argue for that in a moment. But the key point at this point is that in fact we have managed to peel off the n plus 1th order term, and it is a degree n polynomial which we can expand in this manner on the right hand side. So in order to show that all these lower order terms are 0, so let us consider this integral, right? So the result follows from orthogonality, right? So we know that all these polynomials, together they form a basis, but they are also orthogonal with respect to your weight function in the given interval, right? So to see that these delta I for I less than or equal to n minus 1 are 0, so we consider this integral, multiply of course with w of x, and then you take this x times Cn of x, and then you also put in a Ci of x, and this I can go from 0 all the way up to n minus 2. You will see in a moment why we do this, right? So I is restricted to lie between 0 and n minus 2. If you consider this integral, now there is a way to re-look at the same integral, right? So recast this integral. It's the same integral, but we just shift this x to the right of Cn of x, and then group these two together, x times Ci of x. And now Cx times Ci of x for sure is a polynomial whose degree cannot be greater than n minus 1, because Ci of x is a polynomial whose degree cannot be greater than n minus 2. So if you multiply it by x, this polynomial has a degree which is necessarily less than or equal to n minus 1. But Cn of x is a polynomial which is or degree of degree n, and which is orthogonal to all polynomials whose degree is less than n with respect to this weight function in this interval, right? So immediately this follows that this has to be 0, right? So we see that this function x times Cn of x cannot contain any term whose order is greater than n minus 2, right? So an immediate consequence is that we get this 3-term recurrence. So the key point is that if any of these other Ci's has to appear, it has to appear only from here, right? Only from the second term, because this first term will have no component coming from any Ci of x, not just I less than or equal to n minus 2, but it's for any I other than n plus 1. This is not going to contribute because there's already an orthogonal polynomial with index n plus 1, and every other orthogonal polynomial whose degree is less than or equal to n minus 2, we have explicitly shown cannot appear here. So immediately we have this result Cn plus 1 of x minus some coefficient alpha n x Cn of x is equal to beta n Cn of x plus some other coefficient gamma n Cn minus of n minus 1 of x. So both these coefficients beta n and gamma n are to be determined, and alpha n in fact we already have it. We have got it in this prescription already worked out. So alpha n is just the highest coefficient a n plus 1 of this expansion for Cn plus 1 divided by the highest coefficient in the expansion for highest coefficient term in the polynomial Cn of x, right? So basically we managed to use this clever argument and use this peeling off operation to show that necessarily there is this way of combining this n plus 1 degree polynomial and nth degree polynomial in this precise manner to get this 3-term recurrence relation. So it turns out that specific polynomials satisfy a separate 3-term or some number of term recurrence relation, which we will come to when we discuss individual polynomials, also derivatives involved and so on. There are other interesting recurrence relations which can be worked out, but this is a very general result. It holds for any of these different kinds of orthogonal polynomials which we will look at. Okay, that's all for this lecture. Thank you.